Fix. Well, good morning, ladies and gentlemen. First of all, I would like to thank all the organizers of this very fantastic meeting, Biohydrology, which is indeed one of the main tasks which we have to better understand what happens. And I'm just here as the president of the International Union for Science, and I would like to convey the best greetings for sure of all the soil scientists. Well, you are all members of them as well. And I think we have a good and have a strong task to fulfill. You know all that we had the International Year of Soils 2015, which was defined by the UN. And, well, we had a huge increase in acceptance worldwide. And based on that, we then thought from the IUSS, come on, let's go on. So we declared just simply in Vienna last December the International Decade of Soils, because being once on the top of the level of recognition and acceptance of ideas, to slow down again because the UN has told, okay, 1 year, that's enough, it's not good for us. And that's why we declared this International Decade of Years of Soils in order to promote soil science knowledge in its broadest view. It's not specialized hydrology or specialized microbiology, what doesn't matter. No. We want to get the information about soils. We want to get the information about soils to all. Not only to the colleagues, we can discuss very perfectly, but none of the politicians doesn't understand us. So we need to discuss to the people outside our community, as well as to the politicians or administrators, because one thing we have to deal with: soils are not renewable, and this is something which we have to push into the brain of people. And this is also something what I would like to show you a bit in the next 3/4 of an hour, to show a bit what is soil and how far do we need to include it also in our conference here. And so we want to know, and everybody of you, and we all know that fascinating picture that I heard about soils are reactors. And we know soils must be well aerated. They must be well transporting temperature, water. There must be a lot of microorganisms available. There must be a possibility to access surfaces. It's not a capacity parameter, the soil. It is an intensity parameter. So we need to have the accessibility of surfaces for the whole processes within soils. Certainly also the capillary wells must be included, also the groundwater recharge, and all this should be optimized in order to get a good yield. Well, soils are needed. And we need them not only today, but also in the future. And we need to feed, for example, 9 billion people in 2050. And we also know that already today, many billion people, 1 billion people are already starving. 2 billion people are malnutrition because of not good food. We need more food in 2050, 70%. And what is even more serious is that we lose per day 300 square meters of soil worldwide. You all know we all came through Madrid. Madrid would go in within 2 days, it's not there. All the people who live there have nothing below their feet. And this is something which we have to consider very seriously. 300 square kilometers per day worldwide is a huge amount which is lost irreversibly. Well, we also have to deal with global change effects, the high flooding, all these problems coming through this global change aspects as well, greenhouse gas, and we could continue on that for a long while. Well, soils are endangered worldwide, for sure. But what to do? And if we now have a look here we are, on the global soil map, how much good soil do we have? Then we can define non-soil, too high, too cold, too hot, too dry, too poor. It's soil affected, it's low in water, mostly coniferous, too wet, or it's tropical. And if we have a look through this picture, one after the other now, so we are now with non-soil, it may be too high, or too cold, or too hot. So here we are with too hot, too poor as well. So that's also with the salt coming next as well. And so you see, we come slowly but surely to a very small area which is left. That is again the tropical part. Okay, it's also gone. So what ends? 13 to 18% of all the land is covered with naturally fertile soils. All the other has either to be improved, which is impossible, or we have to handle them more carefully. And we can also try to define that by the soil types. There are some glacial, some soil types, and so we have here, let's say, only 10 soil types, and I do not bother whether it's well classified or not. It's based on the paper of Bloom and Eswaran from 2004, and it's a little bit more modified. But you see that the land quality classes 1 to 3, these are the most beautiful sites. Okay, we all know mollisols, ultisols, and altisols, they are perfect. But what we find, it's only 11 or 12% of the whole globe is covered by these nice soils, and there are 20% of people living there, a bit more than 20%. Going to the next soil classes, 4 to 6, land quality class, maybe antisols, inceptisols, or vertisols. Okay, here we are with roughly 50%. 50% of people living there for 34% of the area. And last but not least, the biggest area has another 20%, 20-25%. 50% of the whole globe is done with these soils according to that paper, which means we will have a migration from there to other countries. There's no reason why not to go from here to there or to there. So, which means these soils are bad. These areas are not so nice. These areas are perfect. However, overloaded with too many requests for these soils means degradation as well on the best soils. Which means you can also go into the advertisement of Lufthansa, okay, and where do we go? Enough black soil to grow food for the whole world. Now you can even invest in good soils, which is not the solution for the future. It will not work. Land grabbing is a word which is to be seen, as you can see where it goes. So land grabbing is even today a huge problem. Worldwide it will increase even more. So, well, what do we want to know? Well, what do we have to know for a good soil governance? Soil science knowledge for a sustainable environment. I would only give a few examples and then burning open questions, how can we solve them? And we finalize with the conclusions. Well, everybody knows soils are different. And here we have only a few soils from Europe. You all know them, Candisols, clay soils, luvisols. These luvisols or the haptic luvisols, they are very perfect. High in yield and very good. They have a good structure. Structure formation is fine. But you can also go into the deeper part of the valleys. There you have the clay soils. Or in the sandy areas you have the potsoils, or in the peatland you know that these are the lowland or highland peat. You also see a colony soil, which means also there's a migration of particles from the top to the bottom. Below that's a peat, on top is something else. But what you can also see, these soils are always different. They are not the same. They have not the same properties like for nutrient storage, nutrient availability, or the translocation. Some of them are too wet. Some of them are too dry. We know that. So they have different properties, and they have different limitations. and different resilience. Which also means that we have to include not only the physics, but also for sure the physical chemistry or the biology, the redox reactions have to be included as well. Well, in the meanwhile, we have the Sustainable Development Goals defined by the UN and the EU. So we find also suddenly now at least the words of soil somewhere in between. The Sustainable Development Goal number 2 tells something about end hunger, achieve food security and improve nutrition and promote sustainable agriculture. And this is mainly linked to soils. Okay, for sure. Fine. We have to fulfill that up to 2030. Or in SDG 6, it's defined the water, and SDG 7, it's defined the bioenergy. We should have a reliable, sustainable, and modern energy for all. If we see today that all the biofermentators and the problems which are linked to these digestives which come out of these boxes, we destroy our soils within 20 years, latest. Or the SDG 15, for sure, we should combat desertification, and where it's better to say than here. Next to here, there's starts with it. Restore degraded land and soil, including land affected by desertification, drought, and flood. And we should come in the end to the land degradation neutral world. Hey, this is a huge task for all of us, and I'm sure we have to work hard to get it. If we for sure see what happens today in the world, we see that the impact of human activities can be summarized by, let's say, heavy metals, by compaction, by contamination, dispersion, release of toxic substances, acidification, decline of organic carbon, decay or decline of soil functions. Soil erosion it's called, and landslide is for sure to be seen everywhere. And these both are already quite nicely linked, and more than 50% of soil erosion comes from soil compaction. And by that we also can get this gas emission. So we change not only one topic, we change not only one property, but we change a huge amount of following up systems. So soil sealing for sure, it's more and more important. How serious this link is should be shown here. Is shown here, and I'm sure nobody of you can really read it. That's good. But what's to be seen here is the following. If, for example, we add a stress to a system, mechanical stress. So like you and me, I walk, I put a stress on the soil, or the tractor, or whatever. Okay, so what do we change? We change the pore system. Fine, everybody knows it. The coarse pores are declined, but by that the retention curves also change. The fluxes are also changed. By that the vapor pressure is also changed, the vapor flow for sure. It changes the temperature in the system. It changes the organisms, the vegetation, and by that you also change the chemistry and so on and so on. So you see, there's a huge interlink between processes which we have to consider also in that conference here. It's not only one direction. No, you have to think about the whole circle in order to understand the very dynamic soil system. Well, we can also classify soils according to the pollution, the desertification, drought, and if we go here now to Spain, down here, so you may find here for sure water shortage, while in Germany, for example, it's a lot of compaction and so on. Okay, if we sum it up, soil compaction, approximately 35% of the whole area is compacted. Ladies and gentlemen, it does not come back upwards. Loss of organic carbon, 45%. 442 million hectares are already degraded by wind erosion, and 105 million by water erosion. Okay, you can also have some only in Europe. That's only for Europe. That's a very small area here. But you see we have a huge problem in there. So there are cross-compliance possibilities. Every farmer has to fill in some form sheets. But indeed, there's no real measure against degradation. It's not to be paid by the farmer now. It has to be paid by us in the future. So an urgent task for all, we need to quantify sustainable soil properties according to their site and management specific boundaries on various scales and on various details. That's what we have to do. And one of these very strange topics, which all of us know, is soil erosion. And so you know, everywhere you have these quite nice classifications occur. In Germany, for example, so you have nothing to do, no measures, up to 15 tons per hectare a year. There's nothing to do. Only by exceeding this value of 15 tons, okay, pay attention, now we have to do something. But if we compare this number, we even should start here with saying, pay attention, here we are, because soil new formation or new soil formation is less than 0.5 tons per hectare a year, or rough, maybe 0.6 or 0.1, doesn't matter. It's a very small amount. So this is what we can afford to lose. But all what is extra is lost irreversibly and degrades. We can also discuss the topic about climate change. Carbon sequestration, a topic which is discussed everywhere in the world now. Okay, can we, Ratalai did does for sure, a lot of calculations on that. But the main topic which is always asked for is, can soil carbon sequestration mitigate climate change? Everybody believes in this. Unfortunately, we have to say, no, it will not work. It may work with approximately 1 petagram carbon per year for the next 50 or 100 years, but it's nothing, indeed. But we can for sure say, pay attention. If we have more organic carbon in the system, we have better soil structure. And by that, we can have an improved plant growth and so on and so on. So there may be essential, it's an essential parameter for human well-being and nature conservation. But carbon sequestration is not the tool against climate change. So that is something which we have to face. If we can do what we want, there's no chance. Okay, so let's have a few ideas about what should be what kind of soil properties and functions are essential for a sustainable environment and must be included over scales and as a couple processes. I only want to go a bit into this detail in order to show a few aspects. Again, in order to understand the interlinks between processes, chemistry, physics, biology, we can start simply with texture. Okay, everybody of us knows that. But it is not enough to say, okay, this is sandy soil, or that's a less soil, or that's silty soil, or whatever. No. Pay attention. Now we come into the properties of the surface area. The surface areas, for sure, for clay, silt, and sand are quite different. And if you get furthermore go into detail in the clay particles, then you have the swelling aspect, smectite, very intense carbonate, nothing. Now you start with the chemistry, which comes also into the problem of altering soil functions. And then it starts with the valency and the concentration, and now you see that the flocculation power, and by that you end up with, indeed, a lot of interactions. Calcium, carbonate, biota, hydrophobicity, pH, buffering, organic matter, iron oxide, binding agents, as well as all overlaying the soil water potential. The soil water potential is indeed something which is the most important binding force which we have. And this is something which we have to consider more in detail in the Minsky forces in order to get the structure formation, even from the very muddy tidal flat to the marshland to the paleogenetic processes included. So these interactions which are shown here have to be included in order to understand what happens in soils. Because we can also link that for sure to the mechanics. So mechanical processes can be defined quite nicely. They are, for example, interlinked to the water fluxes, as well as the physical-chemical reactions, the viscosity and the surface tension, And by that, linking these both together, you change the whole system again. The name or the word of rigidity. Rigidity of a pore system means how far can we really predict what happens in soils, or where do we only guess what happens? So rigidity of a system is strongly related to suction, to pressure, pore water pressure, to the mechanics, and to the organic as well as a structure formation in total. This has to be known in order to really predict site-specific. And what comes out of those measurements is shown here a bit. Let's say, what is the effect of fertilization on aggregation, strengthening, and water storage? A strange topic, maybe in the first one, but if you see some direct effects or indirect effects by plant growth, there's for sure an improvement of structure. It can be an improvement of structure, as shown here by such bridging, which is more or less a schematic diagram. But what Dr. Holthusen found out in those days, even if we have the monovalent potassium included, the plant available water increases dramatically if you have all other parameters are equal, are okay. But you see suddenly fertilized sites have a much higher plant available water, which means 6 volume percent, meaning 60 liter per cubic meter, which is a lot, meaning 14 days of transpiration. And this can be also explained by, again, a sketch. The pores are too large in the beginning, water is drained immediately, or the pores are too small here in the middle. But okay, now we reduce the size, and now we have suddenly averaged size pores, and that can be even shown on the computer tomograph. In the meanwhile, we have also these data. Okay, fertilizer application seems to enhance water harvesting besides yield increase. This is indeed a topic which can be also included in all our discussions as well. What do we understand about soil strength? Well, we know all that there's a stress strain curve. Strain on the y-axis, stress on the x-axis. And the normal is the virgin compression line, and the other thing is the so-called recompression line. This is what had happened in the past. Structure formation, compaction, and so on. Then the so-called precompression stress. Up to that value, you have elastic deformation. Exceeding this is plastic, meaning degradation. And you can also see the change in the parameters. Until that limit, you have plus minus identical hydraulic conductivity, air capacity, or total porosity, but then it declines. On the other hand, you have an increase in bulk density later on. But, unfortunately, this is not the curve for the soil, but it is a curve for horizons. So we have to understand the soil profiles. Otherwise, we will not get a complete answer, and we have to link it for sure also with the actual stress measurements, which go down to depth and change again. So we have to be left on that precompression stress. Okay, and we all know, and this is something which is so urgent to tell again and again and again. Stresses even of the same amount, 100 kilopascal, but increasing the contact area, go deeper into the system. And the dotted line here means what's plowed. All what's below, it's not plowed again, it's irreversibly degraded. So the same stress applied, you see, it goes deeper compared to the 40, but with the 50 you see the lines are quite much deeper. Which means structure, as well as the discussion about contact area, must be included. And even more important is the shearing. And shearing is nothing what is only available on the traffic lights in the street, but it's always available on all fields. Even if we walk, we shear the soil. This movement, you can see it when horses are running. So the shearing means homogenization. And homogenization means, you see, the same pore system, which is here, that's quite nicely connected all, It's now only sheared, no change in pore volume, but a change in connectivity, and so nothing will flow. It's not the value, bulk density, which can define it, but these are the intensity parameters like hydraulic conductivity, thermal conductivity, or whatsoever, which have to be defined. Otherwise, we cannot define the property of a site. Okay, stress distribution is the deeper, the greater the contact area at a given applied stress, but shear effects are even more negative. These are mostly neglected until today. Okay, watch this. This picture is nice, I'm sure. Everybody likes it. It looks perfect. However, if we now have a look what happens below, even a single wheeling of that combined harvester shows that, okay, the topsoil is completely degraded in extra. Red means degradation in extra. There's a ratio between the contact area as well as internal soil strength. And you see that it goes even down to 80 centimeters depth, and even in 100 centimeters depth, it's still to be seen, but it's not very intense. Green means still okay. But even one single wheeling event is actually even more degrading of soils. So what do we have to know? The burning question is effects on climate change, carbon sequestration, soil water interactions on the long run. Deeper down. Okay, what are the consequences for the functionality and sustainability? Well, this picture is well known. There are lots of papers available, books available all over the world. The links between particles and the three-phase system with the gas, the liquid, and the fungi as well as the chemistry, all these are included, and this makes, in the end, the aggregation. And the aggregation can be also defined like this. You know that circle from the geology. You start from the magma, go to the igneous rocks, sediments, and metamorphic rocks, but you can also do that in continuation to the soil structure. You go from the sediments to the coherent structure. By tensile failure you come to the prism, by shear you come to the polyhedral structure or subangular blocky structure, and if you add too much stress you end in plates. You can also go to the other side, biological processes, but they can also go back to the plates if they are overstressed. And so that's indeed something which we have to think always in circles. These aggregates are not available all the time, but only to the limit, the boundary limit of rigidity, which means the history of the site. If it's more dry or more compressed, then it's gone. We can also find the accessibility discussion, and this is something which is to be seen more intensely, which is to be discussed more intensely in the future. We often discuss about capacity. Everybody of us knows cation exchange capacity. Okay, fine. It is a completely homogenized soil which has accessible surfaces and there are nutrients on it. Unfortunately, you will nowhere have in the field homogenized soils completely as you do it in the lab, which now means you discuss a parameter which is never available in the field. We need to discuss the accessibility or availability. How much of your nutrients, how much of your heavy metals, how much of your water is really possible to reach that point where it can be bound, where it can be fixed. And it's for sure less than the capacity. So we have to think more of the intensity parameters in order to understand soils. And you can also find for sure discussions about, if you compare, for example, complete soil columns or biopore scale or the aggregate scale, you can define for sure also with a computer tomograph, which was done by Mr. Pagenkemper, the pore volume, the pore surface areas. You can also do the relation. But more important for all this is the connectivity or continuity or the tortuosity. So the platy structure has for sure no connectivity vertically. No continuity vertically, but wholly horizontal. That's why water erosion has increased. Biopores, on the other side, they are laughing people. Okay, connectivity is high, continuity is also high. The better the structure formation, the better it is, also for the transport of air, water, and solutes into the soil matrix. This all ends again in the structure. And you see, the structure is, for me, the key point, which we have to understand in order to go to the biohydrology as well, and to understand soil processes. The strength is shown here by the Mocolon failure line. You see a single grain coherent prismatic blocky subingular crumbly structure. It's better the higher. Crumbly structure are best. Platy structure has the highest cohesion, but no angular internal friction. Now you have to link that to the hydrology, for example. We can do it also for other topics. Do we have isotropic conditions in soils? Never. Mostly never. Coherent structure may be a bit of isotropic. Prismatic structures, for sure, water flows down mostly vertical, anisotropic. Blocky structure, okay, where the shearing of the prism coming to blocky or subingular blocky, it goes back a bit to isotropy. The platy structure is completely anisotropic horizontally. So please be aware to think about three-dimensional systems. Hydraulic conductivity is a tensor. Nothing more than this. 3 dimensions, please. So we have to understand these fluxes in order to also predict on all levels the processes in soils. So, okay, aggregation for sure, higher strength, development of different flux directions, but, ladies and gentlemen, again, exceeding that strength of a soil alters all internal fluxes, internal soil properties, the flux intensity as well as the direction. So we need to understand that. And this picture is, well, okay, everybody of us knows the Hagen-Poisson equation. Okay, we do the same calculation as for the students. Here we have the 20% for radius 1.8, so we have a flux rate of 145 liter per hour, and having the same, the smaller diameter, 0.5 millimeter, have only 14. Okay, now we can also compress it a bit more and come down to 80 liter or 7.86 liter. So which means a small change in diameters makes a huge effect on properties. And the same is also true for the plant available water. As soon as you exceed the internal soil strength, you see that the air capacity goes down, and the available water capacity goes a bit up and then down, and the non-available water capacity for sure increases the higher the stresses are. And finally, if you have a look on the ratio between the hydraulic conductivity and the initial value, you can see, okay, until the pre-compression stress it's nice, and then it goes down. The shrinkage indeed does the same internally inside the aggregate. The shrinkage effect on the micro scale does the same trend. On the macro scale, okay, you have a bypass flow as well, and so it's increasing. So accessibility of surface for water, nutrients, gas, and microbes in the virgin compression and proportional shrinkage range gets reduced or heterogenized. And this picture derives from an old paper of Jasinska, and now it's Emilia Romanek, to measure the change in the CO2 effluxes. Exceeding that value reduces the CO2 flux. And on the other hand, we can also see that reducing the CO2 flux increases the CH4 fluxes, which means as soon as you exceed that internal soil strength, you change the properties, and by that the microbes for sure as well. You get a complete anoxic situation, and the CH4 has suddenly increased, or, well, it's increasing from consumption to emission. The accessibility that I already mentioned is finally shown here again. Cation exchange, everybody knows that. Homogenized is that, let's say 100%. This is the value. You measure. If you now do the same without disturbing your soil, but do the same percolation without prior deterioration, you see, okay, for prismatic structure you may end at something like 60%, don't worry, can also be 80 or 70 or 60 or 40. It's rather scattering for sure, blocky structure goes down, and the platy structure, you fertilize, but you suddenly have only 10% accessible surfaces. All the others go somewhere else, to the groundwater. So you pay for the eutrophication of the groundwater. And even the crumbly structure will closely come to the 100%, but even that was not complete. So please be so kind as to discuss more intensely accessibility, which differs depending on soil structure. Cation exchange capacity is not adequate, like the air capacity, like the plant available water capacity. It does not tell us anything about whether it's available, but discuss about the intensity parameters like fluxes. Well, okay, the roots react as well, for sure, and the safety is better here, but even that is not complete. As soon as you apply a too high stress, it's also altering. So there's always a rigidity again, which has to be included as well. So exceeding internal soil strength results in shallow rooting and reduce nutrient uptake efficiency. What are the tasks and the requirements for adjusted land use? Well, again, here we are. It's a bit from the mechanical point of view. We can say, okay, soils are elastic, or soils react plastic. And so then we can also define all what is elastic. Don't worry, do what you want. No rutting starts. But as soon as you start with a plastic deformation, or even with a more intense shearing, you get a complete deterioration of your soil. Lateral bulging also takes place. So you can also do the following. You can tell now to the politicians, pay attention. This is your traffic light system. And you can now start to say, pay attention, here we are. This machine is quite nice, do it, whatever you want. But never do it like this. Because the sites which have these properties, like the mechanical stress is much higher than the internal strength, and if it's too wet, for sure, then you have also a lot of shearing, like homogenization, meaning soils are degraded by your treatment. Avoiding that means go here. And you can quantify that if you understand the process in systems. This is not only true for Europe. The former was for Europe this year, where it was tested very intensely, very often in various areas. But it can be also done in Chile. For example, in the Andic soils, from Dorner, for example, Jose Dorner and his co-workers, and they also have the same problem. You all know that the volcanic ash soils, the Andes soils, are very weak. The bite densities of 0.234 are perfect. But exceeding 1, it's a complete disaster. Which means we need to know the link also again, what they do, bite density with capacity parameters, they do it like this, and they at least define, pay attention, this is what is the maximum what we can allow in order not to decrease, for example, the air capacity of the plant available water or the air conductivity too intense. So you can do it, and you can also define it. You can define the changes in properties as well. That's something which is just running in northern Germany. Having a look on parameters which are always defined, for example, hydraulic conductivity or the air capacity in Europe, it's very often told, okay, you should have more than 5% air capacity, or you have to have a hydraulic conductivity which should be better than 10 centimeters a day. Okay, but if you have a look on the various soil types, on the various soil locations, you easily see already, pay attention, here we have severe problems. And so we come to the point that we have to also to quantify that. And you may see that even in the A horizon we have already some 27% which are degraded intensely, and the B horizon is degraded up to 70%. It's even nowadays, and even these are the so-called best soils. So we can also define various land use systems, arable or grass and the forest soils, you can always see, pay attention, here we are, right at the forest soil, that's for sure, forests are grown there where the worst soils are, or the worst conditions are. But, okay, so you can do all these things, but we have to do it. There are lots of data available, but we should not, and we should analyze them and not only do new experiments and forget the old ones. So we can even define, pay attention, here we are as advisors for politicians or for lawyers or whatever, it doesn't matter. So we can define the so-called, according to the German soil protection law, so we have the precaution value or the action value, and the action value is what has been done in the past. We can't change that. And the precaution value, if we now put in the parameters like air capacity or hydraulic connectivity, or the action value, meaning now you have to stop the present management. You can define that by oxygen availability or hydraulic connectivity, and you can also define soil types for that. But please do it. So in order to sustain soil properties and functions, and more site-related land use and soil management should be defined worldwide. Apply this knowledge, what is available worldwide. Well, this is something where everybody laughs or everybody shakes their head. These equations are well known. Everybody uses them, or if you want to use them, do it. But stop. Stop whenever the rigidity of a soil is not available. As soon as you exceed the internal soil strength, you change the input parameter, the boundary conditions for your equations. You have to start from the very beginning again. This is not there is one equation available, or there's one parameter set available for hydraulic connectivity for a certain, for water fluxes for a certain soil. No. Depending on your specific site properties. Stop. As soon as you exceed these boundary conditions, the mechanical strength or the hydraulic stress, it's the same. Then you change your rigidity, you have exceeded your rigidity, which means we need deformation-dependent saturated hydraulic connectivity. For example, or the water retention, it needs always a void ratio included. And even more problematic is the unsaturated hydraulic connectivity. You have to add the mechanics or the hydraulics as well. Shrinkage-induced changes of properties affect the prediction intensely as well. To determine these properties are a bit difficult. So you have enough to do for the next decades. So last but not least are the very questions. What do we have to know? Soil functionality maps to quantify existing threat risks. Sensitivity map to minimize future degradation processes. Scale-dependent soil management scenarios have to be done. Soil and land degradation discussion and mapping can be based on soil science knowledge. Include microscale that must be done, and the quantification of costs for human activities and following amelioration approaches have to be done as well. Integration of biodiversity in global soil approaches. The thing that we have to do is we have to increase the soil awareness. And with this, I come to the end. We know that land use and soil protection are not conflicting each other if the boundary conditions are considered. Soil degradation must and can be prevented, but not re-ameliorated worldwide. And with the last sentence I would like to stop. The slogan, if you can measure it, you can treasure its need, and it needs more attention. Thanks so much.